So this problem is which particle has a highest penetrating power? And it's kind of funny to say that the answer, the reason that the answer is highlighted because I want to make sure that my answers are correct. So I'm sharing the screen with you onto the one that is having an answers key already. So the C is the answer, and the gamma particle is the one that is on highest energy. And that you can think about as a particle because is a photon is a particle perspective. So this one is just understanding the knowledges, what is the penetration power. So what that means is for electromagnetic radiation, you need to kind of protect yourself by putting some kind of metal block. And the alpha, beta, gamma, they kind of need different thicknesses, and the gamma is the highest one, energy, and that's why it is very difficult to block those gamma rays when there is a nuclear reaction to emit the gamma ray. Okay, so this is number 11, and number 11 is they are saying that oxygen 18. So oxygen 18, what you can think about now is oxygen. Okay, let me pull up an oxygen here. Oxygen is here, and I don't know. You can see the number 8. Right? So number 8, oxygen is I know is a Z number is an 8. Okay, there are 8 protons. So when you see that oxygen means, okay, then the number of neutrons is 10. So that's something that you also, that's something that what you have to think about in your mind. Okay. So what is a missing species when oxygen 18 is generated by bombarding nitrogen 14? So when you say nitrogen, number of proton is 7. And because it's 14, so the neutron is also 14. No, not 14. The neutron number is 7. That's what it is. And then bombard with an alpha particle. So I guess this one is trying to see, you need to have an idea about what alpha particle. That's the atomic number 2 with a mass 4. We call helium. Okay, so that's either you can put 2 plus 1 out is optional, but that's what you see. So that's why you are seeing this here as a N147 with bombarding with a helium alpha particle. So that's the one, and they are saying that oxygen is being with a 18 is generated. Oh my, this problem is also not correct. I need to report to the Scott and Kathleen. So this problem is supposed to be 17. I didn't pay attention to it. So that means you have you have 17. You have 9 neutrons. Okay, so you have 17. And 8, okay? Because that's when they say it. I think the answer goes by the way it's written here. Okay, there are many typos. I'm still getting the typo. Okay, and then so what do you need? Okay, so this is 7 to 8. You just write it 1, right? You got 18. You got 17. You got right there so 1. And then when you see 1. That is for you to see same thing as for you to write on hydrogen, and then the atomic number 1. So this is essentially protons are being emitted, either protons or proton as a charged species. Either I think the answer is acceptable, and so therefore my answer here is D. So number 12, if I'm moving on to number 12, and write a nuclear reaction. Okay, fine. And the nuclear induced fission. fission means you're kind of cracking it's like a cracking an egg, right? So you have this one with a pretty big atomic number. So I can write it as 235 uranium. So where do I know to find the number of 235 of uranium? You don't have to remember. You just have to go and look at, make a light here. Okay, so uranium, you guys find the uranium? I think we have done that before. There we go. Yeah, so that's the uranium. And if you look at the better version of the periodic table, that's a 92. Okay, so this is a uranium here is a 92. That's a 92. So what I'm going to write is on the bottom, it will be a good idea for you to say, okay, number of proton is 92, that's for sure. Number of neutron here is actually 235 minus 92. And if you click on it, that will be 143 neutrons. So I'll like putting something a little notation looks like that. So that make up the whole understanding of the uranium. And so this uranium is now broken into pieces. That's a fission is about. And the xenon and what they call strontium, okay, and 100. So what this information is, xenon and the strontium. And they give you a whole, the mass, 134 and 100. And what you need to do now is by looking at information of the xenon. So xenon is easy to find. This is one of the halogens. So xenon is right there. That's 54. So 54. I'm going to write 54 protons, right? And the strontium is atomic number, where are you? I think I remember finding this one before. So you need to look for this. You might notice number 38. Do I see number 38? Yeah, here. Oh, I'm sorry. Yeah, that's a 38. That's a 38. That's a 38. 38 protons. And then, so therefore, you can find out how many number of neutrons in strontium. 62 neutrons, and that's 80 neutrons to make up 134 and 100 atomic numbers. So they are asking how many neutrons are produced in this reaction. So what that means is there will be something extra, and they wanted to know, well, how many neutrons are going to be coming out. And neutron has a mass and no charges, right? So this is a notation that you have to keep that in mind, but they say how many. Let's look at 92 and 54, 38. If you do that, actually 92 protons, 54 minus 38 is 0. So actually there's no protons being lost or liberated. So that's actually good. It's only the neutrons are involved, but let's look at it, right? So this is a before and this is an after. So I would like to do this way. 133 is what you have before, and you have lost into the xenon form. You have a loss into the, that's the protons, and then this is a neutron 62. And if you do that, 1 neutrons, right? So this is a 1 neutrons that being lost. So there's only 1 neutrons. So how many neutrons are produced? 1. So this answer is wrong. And this one I got confirmed that from the talking to the, oh sorry, okay. So that's a complete view. The number C is wrong. Actually, B is correct, and I got confirmed before I talked to them. But I didn't know the discrepancy of the 17 and an 18 here. And the answer, this one should be 17. Okay, so I will stop here because there are three more problems. I'll just give you a little overview. You can see that half-life is given, and then now they're asking you that how long will it take for the amount of this one to a drop of some milligram. And typically the initial concentration or initial mass is given, and this is the mass at certain period of time, and they usually ask a time, or they give you a time and what is a mass, so vice versa, and that's the one. Okay, so you can think about it and solving it. You can also, this is related to the essentially same problem is, and the week 11 discussion problem number 2 that is already on the YouTube. So you guys can look at it and then tackle this problem for yourself. And this problem is already on LMS. You guys can download the problem from the last year, the previous exam, and this is all onto the web. And number 4 is actually this is a most likely undergoes electron captures, and this is actually related to what I talked about today. If you're looking at the aluminum is if you look at that, aluminum, the Z number, the number of protons are 13, right? 13 protons, and so this makes it aluminum 24. Number of neutrons is 1, right? So 11 neutrons. So that makes it neutron number of proton is 11 from 13. That make it very unhappy. Do you remember my crash course that this element is really the neutron, the minimum amount of neutron that nature wants is the same number as a proton, and if you increase the atomic numbers, the n number goes up. So that's why in the lecture note it will say Z is 1 and up to Z is 20, right? Up to G is 20. And then n over z is about 1.25, for z is 20 to 40, and so this is what is called the diagram that is shown up here, and this one shows the neutron is very, very small. That's what it is. You can see for yourself later. I'm going to solve this one with the students later, so I will just delete this one for now.